Okay.
Thanks. Hello, everybody. Welcome to lecture 4. I'll post the homework solution to the problem that we discussed in lecture 3 on the course website today. Today, I'd like to briefly review the last lecture, then talk about the subfield of fluctuation relations, and then start on the framework of resource theories by talking about resource theories in general. And in the next lecture, we'll dig more deeply into resource theories for thermodynamics. Last time, we said that there are many, many subfields or sub-subfields, depending on how you look at the situation, of quantum thermodynamics. I like to think of quantum thermodynamics as a landscape on a map, and these different subfields form different city-states. We talked about 2 during the last lecture. One consisted of quantum thermal machines. We saw that the first quantum heat engine proposed consisted of a maser, which is like a laser, but puts out microwave light instead of visible light. We saw that what's important about the system is that it's discrete, it has a finite state space, so it can benefit from a negative temperature. But many, many more quantum engines have been proposed, as well as other quantum thermal machines, such as batteries and ratchets. We also talked about quantum clocks. We said that, according to Wolfgang Pauli, there is no time variable in quantum theory, even though position corresponds to an operator. I shouldn't really have written variable, I should have written operator here. Also, usually there's a trade-off between one's ability to keep time accurately with a system and one's ability to extract work reliably from the system. Today, we're going to start on a new city-state, that of fluctuation relations. These can be regarded as within a slightly broader field of stochastic thermodynamics, which is in non-equilibrium thermodynamics, or non-equilibrium statistical mechanics. In this field, people like to think about strands of DNA and molecular motors and Brownian particles. These are useful because they strengthen the second law of thermodynamics. First, they're equalities, even far from equilibrium, in which case the second law turns into an inequality. Second, they imply what's really an implication of the second law of thermodynamics. Although people sort of talk about this as just the second law itself. Also, they provide more detailed predictions, as we'll see, than the second law does. Many fluctuation relations have been proved. I'll focus on 2 of them. One is Jarzynski's equality by Chris Jarzynski. Except Chris is very, very modest, so he never calls the fluctuation relation by his name. He always calls it the non-equilibrium fluctuation relation. The other is Crookes' theorem, named for Gavin Crookes. These fluctuation relations concern work. Other fluctuation relations concern entropy production. Here's a story that is an example of a story governed by fluctuation relations, but it has the form of a more general story. Here's the setup. Let's think about a strand of DNA floating in an aqueous solution at an inverse temperature beta. This setup is classical because the first work on this sort of fluctuation relation was classical, and I think that the classical story is rather easy to intuit, but we'll address quantum versions later. Let's define a forward protocol. The strand is initially at thermal equilibrium. So if it has a Hamiltonian or if it can have possible energies E, then it obeys the canonical distribution e to the negative beta E over the partition function. And this has an equilibrium free energy that's a Helmholtz free energy that has this form, wherein the partition function is defined in terms of these Gibbs factors. So we can trap one end of the DNA in an optical trap and then use optical tweezers to stretch the strand. We'll stretch the strand through a fixed distance of length L. This process happens in finite time. And stretching the strand requires some amount of work to be invested. Let's call it W. So this work changes the DNA's classical Hamiltonian from energies. So instead of energies E, we'll now talk about energies E prime. If the DNA sits around forever after this stretching protocol, then it'll equilibrates. Again, to the inverse temperature beta, to a new equilibrium distribution with a new partition function. And it'll have a new free energy. Let's actually call the initial free energy F sub I, so we can call the final free energy F sub F. We repeat this process in many trials. Each time we measure the work required to stretch the DNA strand. Let's analyze this protocol. The amount of work required varies from trial to trial. How come? Well, if the pulling were quasi-static, so infinitely slow, so that the DNA were always in equilibrium, then the work required would be deterministic. The work would be what I'll call delta F, which is that final free energy after re-equilibration minus the initial free energy. But the stretching, it happens in finite time, so it jerks the DNA strand out of equilibrium. The DNA hits water particles randomly and hits different water particles in different trials and in different places in different trials, so there's randomness. So if we measure the work required in every trial, then we can infer a probability density, P of W, such that P of W dW is the probability that in any given trial, the amount of work required will be some amount within a window of length W centered on the value W. Now we can state Jarzynski's equality. It governs this probability distribution. Each side of this equation has an exponential. One has the inverse temperature and the free energy difference. And the other side has an average with respect to the probability density, again, the inverse temperature, and now the work required. The right-hand side we can measure via the protocol I just described. So we measure W in every trial, we infer this probability density, and then we average. This average is defined like so. We can pretend to do a Vic rotation, make the inverse temperature be I times some number tau. We usually like to pretend that tau is in the real numbers so that we can say that this right-hand side is a Fourier transform of the probability density, which means that it's a characteristic function. So to me, the essence of Jarzynski's equality is the free energy difference. The free energy difference is related to a characteristic function of a work distribution. That wasn't supposed to happen. There we go. So if we know the right-hand side, we can infer the free energy difference from Jarzynski's equality. This free energy difference turns out to be useful in pharmacology and chemistry and biology, so people want to measure it. But it's difficult to measure, for instance, because it's a difference of equilibrium free energies. And equilibrium is, as we discussed, an idealized state. You can't exactly reach it in finite time. We could infer delta F directly from just one trial if the pulling were quasi-static, because as we said before, the work would equal the free energy difference. But a quasi-static trial would take an infinite amount of time. Jarzynski's equality implies, as we said before, an implication of the second law of thermodynamics. We can see that by using Jensen's inequality. Which states that the exponential of an average is less than or equal to the average of the exponential. This derives from the exponential's convexity. And I'd like for you to prove it for homework. As a hint, you can do this by plotting the function e to the x. Let's let x equal negative beta w. Jensen's inequality tells us that e to the negative beta times the average of w is less than or equal to the average of e to the negative beta w, which we know from Jarzynski's equality is e to the negative beta delta f. We can take logs. Negative beta times the average work is less than or equal to negative beta times delta f. Then we divide each side by negative beta. We flip the sign of the inequality and find that the average work required is at least the free energy difference. The free energy difference, as we said before, is the work cost if the pulling is quasi-static, and we should expect that if the pulling is slow enough that we don't disturb the system very much, we don't jerk it out of equilibrium, then we can spend the minimum required amount of energy. But we're not going to pull that slowly, so we're going to have to pace them more. So Jarzynski's equality is stronger than this implication of the second law. Let's take a minute-long break and review in our mind's eyes what we just saw and heard. Does anybody have questions about Jarzynski's equality?
So there is one question from Julia in the chat.
Can predictions be made about P of W? We know that P of W satisfies Jarzynski's equality, so you could say that's a prediction about it. And later I'm going to show a typical shape of P of W and talk about some of the properties that it typically has. One question is, how can beta be a complex number? I said that people sort of like to imagine that this tau here is a real number. This is a trick that's often used in quantum field theory. So it's sort of brought in here. You often think of inverse temperature as complex time. In quantum field theory, that allows us to do some very useful things. Not all of those things are done here. I personally have never understood why people don't just say, instead of a characteristic function, this is a Laplace transform, in which the exponential carries a real beta. But it can be maybe conceptually sort of useful to think of the right-hand side as a characteristic function, which really is a Fourier transform. Otherwise, you don't really have to think of beta as a complex number. In the real physical world, beta is a real number. This is just adopting a technique that's, or a convention that's often used in quantum field theory to do other things over there. What would happen if the stretch were too rapid and not quasi-static? Then we would spend more work than the free energy difference. And indeed, that's what happens in reality. Okay, let's move on. Let's progress beyond Jarzynski's equality and return to our DNA strand to define a bit more. We defined a forward process, so it makes sense to define a reverse process. Let's redraw the strand. Now, the DNA strand begins stretched. Still in this aqueous solution at an inverse temperature beta. We suppose that it begins at equilibrium with the final free energy. Well, at least what we called when we were talking about the forward process, the final energy. Now we're just calling this free energy F sub F. We'll let the strand relax against the optical tweezers, which are implicitly here because we need for them to keep the strand stretched initially. We let the strand relax, the classical Hamiltonian of the system changes. Now, the strand performs a positive amount W of work. We're essentially letting a spring collapse. Again, the amount of work is probabilistic, and if we perform many trials and measure the work required in each trial, then we can infer a probability density. The notation is a little bit funny because there's this negative sign here. We tend to think of W as positive. So this quantity here is the probability that in a given trial, the strand performs an amount of work within dW of the number W. Let's also relabel our earlier probability density. Earlier, we defined a probability density P of W. Let's call it now P forward of W. We can now state Crookes' theorem. And to clarify, the apostrophe goes after the S. Otherwise, it would mean that this is the theorem of a crook, a criminal, and we don't want to say that. The left-hand side contains a ratio of the work probability densities. The right-hand side contains yet another exponential. This was discovered after Jarzynski's equality, but it implied Jarzynski's equality. We can move the e to the beta W to the left-hand side, then move the p reverse to the right-hand side. Now we have p forward of W times e to the negative beta W equals p reverse of negative W e to the negative beta delta F. Then we integrate each side over the work. The left-hand integral is, by definition, e to the negative beta W averaged. And in the right-hand side, this e to the negative beta delta F doesn't depend on W, so we can move it outside the integral. This integral equals 1 by the normalization of the probability density. So we have recovered Jarzynski's equality. How do these probability densities tend to look? Now I'll draw the distributions that I actually got from numerical simulations in a paper I wrote with Chris Jarzinski. I actually don't have the identifying information here, but here's some of it. And I think it was published in 2016. On the x-axis, we'll plot the work. On the y-axis, we'll plot probability densities. The reverse distribution tends to be farther leftward and peak higher leftward. Then we have the forward distribution. I'll get to the questions in just a moment. There are some interesting properties to note. First, the curves cross when the work equals the free energy difference. As we can see by substituting into Crookes' theorem. If we substitute in the right-hand side, W equals delta F, then this exponential equals 1. We can move the P reverse to the right-hand side and see that P forward just equals P reverse. So this is another way to extract the free energy difference from these pulling experiments. Suppose that we look at where the work is large, so far out on the x-axis, for example, here. The forward distribution lies above the reverse distribution, or even it's much clearer here. That means that we more likely pay a large amount of work in a trial of the forward protocol than we can extract a large amount of work in a trial of the reverse protocol. We can verify that by looking back at Crookes' theorem. Suppose that the W in the right-hand side is large, which means that in the forward protocol, we will pay a large amount of work. And in the reverse protocol, we will obtain a large amount of work. See, if W is big, then W minus delta F is going to be positive. And exponentials grow very quickly with positive numbers. So this is a large positive number. So in order for this equality to be satisfied with the fraction on the left-hand side, the probability of paying a large amount of work has to be much larger than the probability of obtaining a large amount of work. So in the spirit of the second law, we usually can't break even. We tend to lose more than we gain. If the protocol is quasi-static, then these probability distributions, I'll just express both of them as P of W. Well, I guess it would be more useful to, let's say, each density is a delta function. Because we know that the work required will always be the free energy difference. Something else that's interesting about these is in pretty typical cases, these curves are not Gaussians, which we very, very often expect in statistical mechanics because of self-averaging of many, many particles. But our system doesn't have very many particles, so we shouldn't necessarily expect the Gaussian that comes from large numbers. In fact, these distributions have large tails, fat tails. I see that there are some questions. Let's take a look at those. Gabriel, is anyone raising his or her hand?
No, not yet. Only the questions in the chat.
Okay. One question is, are there fluctuation theorems for heat instead of work? Basically, there are fluctuation theorems for entropy production. Could you talk about the negative sign again? I'm guessing that means the negative sign in the reverse work distribution. This negative sign convention is rather funny, and I always have to double check myself, but it means this quantity here signifies the probability that in a given trial, the DNA strand will output an amount of work that's close to W, and W tends to be positive. So this is just funny notation to get used to. What is the point of return we are aiming in the reverse process? In the forward process, we began with the DNA strand unstretched. We allowed it to be like a spring that's not experiencing any force on it. It's in its relaxed position. Then during the forward process, we stretched it through a given length. In the reverse process, we start with the DNA strand stretched through that length, and then we let it retract until it's relaxed again. So just as relaxed as it was at the beginning of the forward protocol. If we are performing the reverse trial, we assume that the system starts in equilibrium, and then we let the DNA strand relax. Then we can remove the optical tweezers. After that point, if we want for the system to get back to equilibrium so that it has an equilibrium free energy, F sub I, then we need to let the DNA strand sit around basically forever. One question is, from now on, everything we saw belongs to statistical mechanics and not quantum mechanics / thermodynamics, right? We've been talking about Crookes' original theorem and Jarzynski's original theorem. Those are classical, and I think that it's particularly easy to understand these things through the story about the classical DNA strand. That's why I'm providing background information about the classical versions of these relations. Shortly, we're going to talk about quantum versions. And what you would like to categorize these as far as thermodynamics or statistical mechanics goes, is up to you. In an earlier lecture, I talked about how traditionally there has been a division between statistical mechanics and thermodynamics. Some people like to say, anytime we deal with density operators or probability distributions over phase space, we're dealing with statistical mechanics. But this has the spirit of thermodynamics because we're interested in work. And there is a subfield called far from equilibrium thermodynamics. Ilya Prigogine won a Nobel Prize for it, and he used the term non-equilibrium thermodynamics. So if we want, we can regard this as being in non-equilibrium thermodynamics or in statistical mechanics. It's up to us. For a continuously driven system, will the equilibrium state correspond to the steady state? And in that case, what is the reverse process? Here we're talking specifically about a protocol in which during the forward version, we start with a DNA strand, or we start with the system in an equilibrium state, and then we apply some force according to a predetermined schedule, and then we stop. And in the reverse process, we do the opposite. If you want to define a different protocol, it sounds like that's what you're suggesting, then you can analyze that particular protocol that you have in mind and see whether you can come up with some other equality that involves the free energy difference. Some upshots of fluctuation relations. Include the following. First, they can be useful. As we saw from finite time non-equilibrium experiments, we can infer a difference between equilibrium free energies. I should add, there is a caveat. Jarzynski's equality involves this average. Some terms contribute more to the average than other terms. The terms that contribute more or are dominant are unfortunately very rare. So you will see those, you will be able to estimate the probability density of those terms from very few trials. So there is also some difficulty in using Jarzynski's equality, but work has been done about how to infer delta F from this equality rigorously and to estimate the error. This paper with Chris Jarzynski is aimed at addressing that problem using some of the tools of modern information theory. Fluctuation relations also have a nice foundational flavor in addition to being useful. These are exact equalities about far from equilibrium statistical mechanics. Such equalities tend to be rare because far from equilibrium statistical mechanics tends to be messy. And as we saw, these equalities imply implications of the second law of thermodynamics. So they connect very closely to the foundations of thermodynamics. Third, you can connect this theory to experiment, as with DNA strands. These fluctuation relations have been tested experimentally. Platforms used include DNA, RNA, colloidal particles, trapped ions, single electron boxes, and probably a fair amount more at this point. Okay, let's take another minute-long break to give our eyes a rest from the computer screen. Let's move on to quantum fluctuation relations. first of all, we should be aware of the danger that this realm requires us to consider quantum work and heat. The system of interest is exchanging heat with a bath, and its Hamiltonian is changing. So we face the crisis that we discussed in an earlier lecture. Again, everyone seems to have his or her own favorite definition of work and heat, which potentially can lead to his or her own favorite quantum fluctuation relation. I'll present one example that's at least widely known. Proved by Halpern. That appears in this paper. Here's the setup. We have some quantum system of interest, S, that has an initial Hamiltonian H, which has this eigendecomposition. There is again also a bath, which we'll call B, at an inverse temperature beta once again. The system of interest begins at thermal equilibrium. I'll get to questions at the end of the subsection. Some people were saying that it was very distracting for them to have a lot of questions throughout the entire lecture. So I'm going to try to hold off on answering questions till the ends of subsections. So thanks for your patience. Let's define the following protocol. First, we disconnect the system from the bath. Then we'll measure the system's Hamiltonian, yielding some outcome. Let's say it's labeled by J. Then we perform our work. We evolve the system with a unitary U, while the Hamiltonian changes to a Hamiltonian H prime, which has this eigendecomposition. Then we measure the energy again. But now we're measuring a new Hamiltonian. We receive some outcome. Let's say it's the kth. We define a protocol. Now we get to define work. The work on the system of interest is defined as the final energy outcome minus the initial outcome. This scheme for defining work is an instance of one of the strategies that we talked about in an earlier lecture. And this instance is called the 2-point measurement scheme. Because the energy is measured at 2 points in time. The scheme's name is often abbreviated as TPM. Now let's derive Jarzynski's equality. Let's start with the left-hand side of Jarzynski's equality. By definition, this average of e to the negative beta w equals a sum over the possible values of the work times a probability distribution times e to the negative beta w. Now we have a sum under the assumption that the possible work values form a discrete set. So that's what we're assuming here. Because even if the system is quantum, well, this is just an assumption we're making here. So each value of w, we said equals e prime k minus ej. we can make that replacement. And the sum is going to be over the ej's and the e prime k's, whose difference is w. Now we have a sum over the work values and a sum over the indices j and k, such that e prime k minus e sub j equals w. Then this probability distribution over the possible work values turns into the joint probability distribution that the first measurement yields outcome j and the second measurement yields outcome k. Then we have our exponential and we replace the work with the energy difference in the argument. This joint probability distribution we can write out more fully. It's the probability that e sub j, let me write it like this first. It's the probability that our first measurement yields e sub j times the probability that our second measurement yields e prime sub k if our first measurement yielded e sub j. We can write that out in more detail. The first probability is given by the Boltzmann distribution, the Gibbs distribution. The second probability comes from quantum mechanics. If the initial state was e sub j, and we evolved with this unitary, then the probability of obtaining this outcome from the second measurement is given by this square modulus according to Born's rule. We can rewrite the square modulus as a trace. First, let's write it out in full. We have an e prime k u, ej that's now an outer product, u dagger, e prime k. We will rewrite that as a trace for future convenience. A trace of the outer products of e prime k's times our unitary times the outer product of ej's times u dagger. Let's substitute all that. If I can move upward. No, I didn't want to do that. There we go. But I still can't move upward. Just a moment.
So the iPad zoomed in a little bit. Okay, yeah. So it's back.
There we go. Yeah, my iPad was misbehaving. Sorry about that. So let's substitute this that we've just written below into our upper equation. The left-hand side of Jarzynski's equality equals, we can take these two sums and combine them into just a sum over j and k. Now we have a sum over j and k with our Boltzmann factor. Then what used to be the e to the negative beta w times our trace. We can combine these two exponentials into an, the iPad is misbehaving again. Here we go. The ej's cancel. So we're left with an e to the negative beta e prime k over our partition function. And also the trace is linear, so we can move the sums and the exponential inside. This left-hand side becomes 1 over the partition function times a giant trace. First, we have our sum over the k's with our exponential in here, and our outer product. I'm going to partial this factor off. We have our unitary, and then our sum over j with the e sub j outer product. I'm going to parcel that off, and we have a u dagger. This second parceled off factor is a resolution of unity. So this u on the left-hand side can cancel with the u on the right, the u dagger on the right-hand side. What we have in this parceled off factor is just the partition function associated with the final Hamiltonian. So our average e to the negative beta w is z prime over z. For an equilibrium state, the free energy equals -1 over the inverse temperature times log z. So the partition function equals e to the negative beta f. If we substitute into the equality that we just derived, we will find that, as expected, the average of e to the negative beta w equals e to the negative beta delta f. That's the Tasaki-Jarzynski equality. Let me take a look at the questions in the chat. Is there any chance that everyone agrees on the same definitions of quantum work and heat at some point? It's possible. I'm a little doubtful. I said my personal opinion is many different definitions make sense in different contexts. Why not just use springs and fluids? Potentially you could. The DNA strand you could regard as a spring. For homework, I would like for you to prove what's called the Tasaki-Crookes equation, or a quantum version of Crookes' theorem using this formalism. In order to do that, we will need to define a reverse process. We've seen one way in which we can extend Jarzynski's equality, and we will see how we can extend Crookes' theorem to the quantum regime. Lots more work has been done on fluctuation relations since Tasaki's work was done. And for instance, there are a number of people who have thought about coherences relative to the energy eigenbasis in fluctuation relations. Here are a couple of references. I'm not going to talk about them in detail. One is by Johann Oberg. The other is by David Jennings's group, led by Zoe Holmes. And other works have been written. Let's take another minute-long break and rest our eyes and turn passive learning into active learning by reviewing what we just saw and heard. Are there any more questions about the quantum Jarzynski equality or the 2-point measurement scheme? One question is, I may be wrong, but a lot of what we did is not Lorentz invariant, right? Will that not be a problem? In this case, we're dealing with quantum mechanics, so we're not worrying about relativistic type invariances. People have been studying fluctuation relations in the context of quantum field theory, where that might come into play more. So there are some references about that. If people are particularly interested in fluctuation relations in quantum field theory, then feel free to email me later and I can point to a couple of references. In which step of the derivation, when did you start to consider that the system was equilibrium? In this forward protocol, which we just call the protocol in this case, here we go. We supposed that at the beginning, the system was in equilibrium with the bath. Then we performed the stretching protocol and the system came to be out of equilibrium. In fact, the system was disconnected from the bath before I said pulling protocol, but whatever protocol it is that invests work in the system. Let's begin on resource theories, which we'll talk about a lot more during the next lecture, the next few lectures actually. I will often abbreviate resource theory with RT. What are examples of resources in your personal lives, in your universities, in your countries, or on Earth generally? Type your answers into the chat. What are examples of resources? Energy, yes. Money, yes. The sun, yes. We get energy from that. Coherence, yep, that's useful to quantum information scientists. Humans, people are resources. Food, definitely can't function without those. Water, very, very important. Supervisor, question mark. If it's a good supervisor, yes, that is a resource. Sleep, I agree, very important. That is necessary for most things. Oil, also a resource that drives a lot of geopolitics. Another example in quantum information processing is entanglements. Yes, to those of us who need to do calculations as theorists, paper and pen are important. Coffee, yes, there is that saying that mathematicians are machines for turning coffee into theorems. So the coffee is the input, it is the resource. Lots of people agreeing about coffee as being a resource. All of these are spot on. So yes, these are all great examples of resources. So what more abstractly is a resource? So what are some of the qualities that unite these examples that everyone has been giving? What makes these examples of resources? They are consumable. Yes, there are things that we can use. They're hard to obtain. That's a way of saying that they're scarce. They have some intrinsic value. Yes, they are valuable, in part because we can use them. And because they are scarce, we don't have infinitely many of them. Yes, they're limited. Yeah, that is all spot on. Clearly, resources are prevalent in our world. They're prevalent in our way of thinking. So it makes sense to have a framework for dealing with them. we might want to quantify resources. For example, suppose that I'm a farmer who has a bunch of wheat, which is not going to be very well drawn. If I have a bunch of wheat, I might want to know how many bushels do I have for some standard size of bushel. We should also be able to compare resources. For instance, two bushels are clearly worth more than 1 bushel, but sometimes the comparison isn't always that clear. We can identify which resources can transform into which others. In quantum notation, is this possible? For example, one transformation that is possible is if I have 2 bushels, then I can throw away half of its value and retain just 1 bushel. Which resources can't transform into which others? Now, if I have just 1 bushel, then I can't turn it directly into 2 of the same size. If a transformation is forbidden, like in this case, actually, let me notate this a little bit differently. If this transformation is forbidden, but I can pay some cost to effect the transformation by putting in something like work, then how much do I have to pay? In general, a goal when we're dealing with resources is to figure out what is possible and what is impossible. The resource theory framework is a framework for addressing these questions. It's a toolkit, a mathematical and conceptual toolkit developed in quantum information theory. It consists of simple models for situations in which constraints restrict the systems we can access. And the operations we can perform. A resource theory typically has 3 components. First are the free states, or depending on which resource theory we're using, systems. We imagine that there's some agent operating in accordance with this resource theory who wants to perform transformations. And this agent can access as many of these free systems as he or she wants without paying any cost. For example, imagine a thermodynamic agent in an environment at a fixed temperature T. The agent can easily access systems in that environment that are at thermal equilibrium relative to that temperature. Another component consists of free operations. These are the operations that are allowed. They obey the constraints imposed on our agent. For example, in that thermodynamic story, well, we're always constrained to conserve energy as far as we know in our universe, but especially in thermodynamics, we're constrained to obey the first law of thermodynamics. Everything that isn't free is a resource. It's scarce and potentially valuable. For example, let's consider that thermodynamic setting. Suppose we're in an environment at a fixed temperature T, and suddenly someone hands us a much colder system. We can let heat flow from one system to the other, and from the heat flow, we can extract work. Work is valuable. For instance, we can use it to power a car or charge a battery. So this system that was not at thermal equilibrium relative to the ambient temperature serves as a resource. Once we model our favorite system in the resource theory, we phrase the problem in terms of free states, free operations, and resources, we can derive answers to the questions that we wrote above. Recently, a thorough review has been written about the resource theory framework. It's by Gilad Gur and Eric Chitambar, who know resource theories very, very deeply. So I recommend this review. During our next lecture, we're going to talk about resource theories for modeling thermodynamic contexts. Looks like someone raised his hand. Gabriel, would you mind unmuting him? I think that's a he.
I don't see anyone else anymore. I think they probably raised it because the iPad was not updating, but I think now it's back. Like we had 2 lectures ago that the iPad started sort of becoming intermittent, but now it seems to be working fine. But I don't see anyone the hands raised anymore.
Okay. Yeah, I'm sorry about the iPad problems. I have not given lectures with an iPad before, and I also can't tell when the iPad isn't working properly. So I'm sorry about that. I'm glad to hear that it's working properly now.
Yeah, no, it's okay. And last time we just unshared the screen and shared again, it was fixed. So at least we try that again if it's necessary.
Okay. Looks like Roberto raised his hand. Would you like to unmute Roberto if you can see a hand raised?
Yeah, Roberto, you're live?
Yes, do you hear me?
Yes.
Yep. Okay, so for instance, your example in the free operations. So I would think that when I hear free operation, I would think that is something that I can do for free, so I wouldn't create resource. However, in your example, obeying the first law, I think that you can perform some work, for instance. So that's my question. Like in a free operation, you have to be unable to create resource, or is anything that obeys the restrictions that you put in your scenario?
There are a few ways of answering that question. In our case, the free operations also involve being able to take free states from the environment. So you can draw a system that's at thermal equilibrium relative to the ambient or relative to the environment from the bath and move any and perform an operation that conserves energy. If you have only thermal equilibrium states, then a theorem shows that you can't extract any work. And this is referred to as complete passivity. If you're interested, then feel free to email me and I can send you a reference about this. We're going to talk in more detail about a set of operations that we can regard as free. In this resource theory, I'll write out the math, so hopefully things will become more clear. There's another way of approaching the resource theory framework, which is suggested by your question. You could specify a set of free operations because it's physically reasonable to think that someone can draw a system from the bath and perform an energy conserving operation and then throw away part of the system. Instead, you could allow to be free all the system, or excuse me, all of the operations that fail to create a resource or that say just preserve the Gibbs state. There are different choices of free operations that we can choose to be our class of free operations. Some of those classes are more physically realistic. Some of them are less physically realistic, but more mathematically friendly. And those different classes of free operations are talked about in Gilad and Eric's review. So if you want more information about that, I recommend checking out that paper.
Okay, thank you. Thank you very much.
There's also a question by Soham. I don't know if you want to answer it now.
Sure.
Hello.
So Soham,
Hear me?
Mm-hmm.
Okay, so my question might be a little different, but so I was thinking about the driven systems. Do you know of any literature in which people have derived such fluctuation relations for driven systems?
Let's
Are you aware
see.
of
So we
any
have a
such work?
system, we talked about a system in which we pull a strand of DNA or invest work to change a Hamiltonian. That investing of work is thought of generally as a drive. Maybe if there was a question from you earlier, maybe I misinterpreted it when trying to figure out what you meant. But we usually think of that process of inputting work as driving the system.
Yeah, no, so what I mean by continuous driving is suppose it's a protein which is attached to a cantilever. And what I'm doing is I'm continuously pressing and stretching the protein in a viscous material. So there is a loss due to viscosity as well as there is a drive. Now, is it possible to think of a fluctuation relation in this scenario where a system is continuously being driven by a, say, sinusoidal oscillation? Or are you aware of any work that has been done along these lines?
So I'm afraid I didn't hear the entire question, but I think it falls under the paradigm that we discussed. We have a system that, well, in the paradigm we discussed, the system starts in equilibrium, although there have been works that extend fluctuation relations to different initial states. And then the system is driven, so work is performed on it. So although I didn't hear everything, it sounds as though the story you described falls within the paradigm we discussed. Also, I'd like to mention to everybody else, now I'm just going to take questions for a few minutes in case people have questions about what we just discussed. So if anyone doesn't have questions and doesn't want to listen, then please feel free to head off and have a great weekend. I'll see you guys on Monday.
So any questions?
Kay Sawada raised a hand. Would you like to unmute Kay?
Hi, Kay.
Hello?
Hello.
Can you hear me? Okay. Sorry if this is a silly question, but is it cheating on the homework if we check these original articles for more details on these calculations and the physical principles?
I would recommend trying the problem yourself first. And if you're having trouble, then to read the paper. And in general, I think that is a great impulse to want to get more background information. Since these homework problems aren't being graded, that's okay with me. I do recommend trying them first to see if you can put things together yourself. But it's great if you have this impulse to learn more about this set of problems as a whole. So I do encourage you to look at the literature if you're interested.
Mm-hmm. Thank you.
Cool. Any other questions? So there was one kind of provocative question from Camille Latoun on YouTube. Maybe I can convey that. So he was actually asking this about the Jarzynski equality. And so he was saying, okay, this is a provocative question, but is the Jarzynski equality really stronger than the second law? And the arguments that he puts in is because usually we only care about the average work. That's the first argument. And the second argument is that if you want Jarzynski equality, you have to do an infinite number of experiments to get the work distribution.
As I mentioned, so there are a number of ways of approaching this. One is you can say this is an equality for systems even arbitrarily far from equilibrium. And the second law generally is an inequality. and outside of equilibrium, it is strictly an inequality. So in that sense, Jarzynski's equality is stronger. The second law implies that the average work required to perform a protocol is at least as great as the free energy difference. Also, Jarzynski's equality implies that there are some people out there, well, okay, the vast majority of people whose papers I've read say that this average delta F is this average W being at least delta F, that is the second law. According to my understanding, you can derive that inequality from the second law. So I think those people would say that Jarzynski's equality actually implies the second law, but I think that what's really correct is to state that Jarzynski's equality implies what is actually an implication of the second law. I agree that very often what we're interested in is the average work. We're not always interested in the average work though. And in a lot of cases, we're interested in being able to predict about a single trial. In these cases, we can use Jarzynski's equality in a way in which we can't use the second law. But if you only care about averages, then go ahead, and if the second law gives you all you need, then you can use just that and not worry about the extra information provided by Jarzynski's equality. Yeah, I mentioned that there is a need to be careful when you're trying to infer the free energy difference from Jarzynski's equality, because this average, because of this average, let me see if I can write. No, apparently I can't write. Just a moment, let me try to fix this. Still no. Oh well, hopefully you can see Jarzynski's equality up here. On the left-hand side, we have that average. As was pointed out, in order to calculate or to infer that average perfectly from experiments, we need to perform infinitely many trials. In most cases in science, since we only ever have finite resources, finite time, we tend to estimate from experiments quantities with finite precisions and then calculate the precisions. In the case of Jarzynski's equality, there is this subtlety or this difficulty that the terms that contribute the most to this left-hand side are terms that carry probability density values that come from very rare events. So it's very difficult to estimate those probability density values. But as I said, and as the arrow below indicates, there have been works on mitigating this problem and quantifying the error and giving experimentalists tools to be able to make the error as little trouble as possible. That is definitely a hang-up in the use of Jarzynski's equality. It's not immediately clear to me that that makes Jarzynski's equality weaker than the second law. From the second law, you could extract the free energy difference from infinitely slow trials. You could do the same thing with Jarzynski's equality. I agree that it's a useful exercise to think about what does Jarzynski's equality give us, what does the second law give us, and how do we compare these two sets of information?
Great. So as Camille said, this is indeed a provocative question.
Yeah, I think it's a good idea to think in that direction.
Okay, I see also a couple more questions in the chat from Thales and Diego and Nicolas.
Had we taken work as an observable in a Heisenberg picture, then we would obtain different values for the left-hand side of Jarzynski inequality. There is a paper by, let me see if I can write it below, Tochner, Lutz, and Hungy. There's a paper by Tochner, Lutz, and Hungy, which is very short but very important, in which they argue that the work is not an observable. That, yes, is mentioned in the question. In your opinion, is there any situation in which we can assume work as an observable? Why, yes or no? I refer to I think of work in thermodynamics as characterizing a protocol. I think of observables as properties of systems. Protocols are different from systems. So let's say I have not yet come across a situation in which I think that it's the best idea to think of work as an observable. As a scientist, I have to admit the possibility that someone could someday change my mind by coming up with a different situation in which it makes a lot of sense. What about equilibration time for closed quantum systems? In Crookes derivation, we have considered that the system equilibrates after running the protocols, but this should require some finite time. If we're talking, okay, suppose that we're talking about the protocol for Crookes theorem or Jarzynski's equality, then we said that once we perform our work, for example, stretch the DNA strand or let it unstretch, if we let the system sit around forever, then the system will come to equilibrium. But that isn't a necessary part of the protocol. All we really have to do is perform the work investment or work extraction process, because all we need to measure in a trial is W. And the reason why I said at the end of a protocol, if you let the system sit around forever, it'll reach equilibrium, is for the sake of being able to define delta F. Again, delta F is useful for some people, so it makes sense to define it. And in order to define it, I had to explain what would happen if the system would sit around forever, but you don't actually have to let the system sit around forever to reach equilibrium. Great, lots of thoughtfully posed questions. Thanks very much.
Okay.
So I'll wish everyone a great weekend, and I'll see you on Monday.
Great. Thank you so much, Nicole. Have a good weekend. Thank you, everyone. See you Monday.